All right, so these were all on the midterm, so people can ask questions about them, but let's jump to, I think we can, if we can review all of these in the next hour and a half, all right? So balanced trees, all right? Oh, it didn't look, is that what you wanted? Oh. This just says, right? They're various, you're doing it in an ordered array or an unordered array is bad, right? It's motivating. We want to do a binary search tree because it's log-in operations. And then later, and heaps are a little faster. And then we're going to do hashing, which hashing can try to do these insertions and deletions in constant time, right? Everybody kind of know this is the big picture of why we're doing these operations. Everybody good? So what I'm going to do here, seriously, this is important to you. I'm going to talk, and if you don't understand anything, don't be shy, holler, okay? All right? Because I don't know where the challenge is going to come. All right? This is kind of... All right, so a binary search tree, if you kind of scan it left to right and not worry about how high you are, you get them in order, right? Everybody sort of see that? 2, 4, 6, 8, 10, 12, 14, right? They're in order. And the property is that I'm really big on loop invariance and systems invariance. So I really think that's the first place to learn any of these things. What are their invariants? All right? You should just know the invariants. And what's the invariant of a binary search tree? You should just know that it's a binary tree with the property that you take any of its nodes and everybody in its left subtree is smaller or equal, and everybody in its right subtree is bigger or equal. And the reason we put equal on both sides is so that if the whole tree is 25s, we can balance it, right? And why is this so great is because we can do binary search on it, right? So if you're looking for the 17, either iteratively or recursively, you look at the root and the 17's to the left, right? You look at the 25, it's to the left. And then, oh, I found it, right? Everybody see how you can just do binary search. And what's the running time? It's the height of the tree, right? Everybody buy this? Yeah? No, it's the height of the tree. All right? So then that comes up and asks, well, what's the height of the tree? And if it's balanced, it's log n. If it's not balanced, it could be really bad, right? So then we're going to get into techniques for keeping your tree balanced, all right? But we're going to do that next, all right? What are we going to do now is we're going to talk about inserting and, right? So, I mean, I can talk about what I've done on tests in the past, right? I haven't made up this test yet, right? In the past, there's been trees like this, and they've been binary search trees, and they've been AVL trees. What is an AVL tree? It makes it more or less balanced, yeah? I think we've been over this a million times. I'm going to put out questions. The other professors are going to put out questions. No question will go on our test that I haven't approved. And, right? So I mentioned this kind of question to Jackie, and he says, yeah, pictures are good, right? I said, if you were doing insertion, you're doing binary search trees, are you going to have code or are you going to have pictures? And he said pictures, right? So this is what I've done in the past. I've had a tree like this. You look at it and you say, I might ask, convince me it's a binary search tree. Convince me it's an AVL tree, meaning it's more or less balanced, right? And you check, does it have the right properties, right? And then I say, add a number. And then you have to know to both how to put it in it and how to rebalance it, right? And draw the new picture, right? So you should definitely know how to do that, right? Somebody was asking like depth first search and breadth first search. What question we might do there? Well, at this point in your lives, you should know depth first and breadth first search. And I don't know if the other people have done it, but if I were going to add an extra questions, it would be about things like loop invariants, right? Because I'm pretty big on loop invariants. Or if we were going to do depth first, I might say, here's a graph. Do depth first search, and what order do you find the nodes, right? Do breadth first search. What order? Doing questions, right? So I like two types of questions. One are thinking questions where what's the loop invariant? How do you maintain it, right? How do you do recursion, right? You trust your left friend, you trust your right friend. And do it questions, right? And even the do it questions, right? If we're, here we have a linked list, right? I'd say, hey, show me how you insert something into a linked list as a stack, right? What would you do? You would draw a picture of the linked list prior to the insertion, and you make it look like the loop invariant, right? What is the loop? You should know what the loop invariant is. It's a linked list with a pointer at the first for a stack. Why? Because we don't need the back. If you threw the back in for good luck, okay, it won't hurt us, right? Okay, this is what our linked list, our stack looks like, right? And then what you do is you draw, right? This is 1, 2, 3. Then you draw a picture of it. 1, 2. After you push something, right? Now I know this is my loop invariant. This is, what have I done? My loop invariant was true. I did the code of push. I made progress of this code, and I maintained the loop invariant, right? So I have this picture, and I have this picture, right? And then people ask, is there going to be code on the test? Well, for me, there's going to be little bits of pseudocode, right? Can you give me code that moves me from this picture to this picture, right? You need to be, yeah. If I make you do a proof, you can do proof by picture. I can't imagine what things I would make you prove, right? Right off the top of my head, I can't think of ever given anything that looks like a scary proof. All right? All right, so let's now do this example, right? Here's a test question. There's a tree. Is it a binary search tree first, right? And you can say, well, it looks pretty weird to me. But one thing, if you scan it left to right, right, they're kind of in order, right? Or you can test, you look at any node, say 11, all its left children are smaller, all its right children are bigger. So you do a quick check, and you say, yes, this is a binary search tree, right? And we happen to number them 1 to 12 so to make it more obvious, right? And then we're trying to insert 10. So what you do is first, it might be there already. So you look where it's going to be. You start at the root, bigger than 1, it's smaller than 11, it's bigger than 10, right? Yeah, so it's going to go over Where's it going to go? You find out where it goes, right? And you go right from 9. And what do you find? You find an empty tree, right? You find an empty point. 9 has a right empty pointer. So you don't go down there. What do? You hang the 10 off of it, right? Everybody buy that? You can always do that, right? You go until it's not there and you put it there. It becomes a leaf, right? All right, now, how do you delete it? Well, if you want to delete 4, 4 has this magical property that it only has one child, right? And you'll note that everybody in the 4 tree is less than the 8, right? All right, so if we delete the 4, then these guys, right, because it doesn't have 2 children, it only leaves us with 1, right? And that 1 can slide up there. Why can it slide up there? Because they're all less than 8, right? Everybody get that? All right, so now, what happens if we want to delete the 3? Well, the 3 has 2 children. So if we deleted it, now we have 2 things to deal with. So what we're going to do is we're going to find the thing that, the smallest thing that's bigger than 3, right? We're going to go bigger than 3, but smallest. So how do you do that? Well, you're going to go bigger, you go right? From 3, you go over to 11. Now you're in the tree of all these things that are bigger than 3, right? But we want the smallest such thing. To get things smaller than 11, you go left, 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 right? And you can't go left forever because it's not an infinite tree. So you got to hit something like 4 that doesn't have a left child, right? And that's great. So we can delete, right? We can take the 3 and we can replace it with the 4. Why is that? Well, the things on the left of the 3 aren't a problem because we made the 4 bigger, right? And the things that are on the right of what was 3, well, 4 is the smallest of those. So it's okay that we put it at the top, right? Does that make sense? Right, so that was legal. And then we're back to what do we do with 6? Right, everybody buy that? All right. So I'm thinking about deleting a lot of these slides. All right, yeah? You bring 2 somewhere else? Yeah, but we also are trying to keep things more or less balanced, right? If 2 was a big tree and I moved it down, 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 I might be making my tree, I might double the size of my tree, right? Another thing about this method is the tree it gets at most 1 shorter and at most 1 longer, right? Yeah, but there's no, because 2 is bigger than 1. Yeah, yeah. All right. All right, so Mr. A and Mr. VL, or something like that, came up with this definition of almost balanced. All right? For every node, you calculate the height of the left tree, and we're counting number of nodes, right? That's 2. And the height of the right tree, that's 3. And the difference between those can be at most 1, right? So in this case, right, 2 minus 3 is minus 1, right? Absolute value is 1, right? And so then you keep seeing these other guys, right? And that's the, right? I thought we did more examples, but. All right, so we did all of these things here about how people think about it, but I think we can go right to this tree. We could delete all those slides and come right to proof by a single example where we, if your goal is, yeah, let's just come right to this example and see what we did. All right? So we're trying to insert 12. So you look, everybody, look where 12 goes. Everybody see where 12 goes? Right? It goes down there. Right? Everybody buy that? Because 12 is bigger than 11. And, right? So 12 goes there. Oh, and let me tell you something else about, about our system invariant, right? These slides I got from a different professor, Andy, after I'd made my other slides, right? And see, he does his different. My slides were storing +1, -1, and these ones are storing the heights, right? And so you can see node 13, well, it has height 3, right? And why do we know it's happy? Well, because this one has height 2 and this one has height 1, and we're maintaining that the difference between those numbers is at most 1, right? So the invariant here, right, you can kind of look, if I give you a picture like this, I don't know, well, the reason I'm saying this is because I don't know if Jackie does pluses and -1s or he does heights, right? But it doesn't matter, because you look and you guess, what's the invariant here? Oh, the invariant, look, it seems they're storing heights. In fact, I would probably put in there, no, we're storing heights, because, right? And then, so what do you want to make sure is if here we're storing heights, and you do your operation, then down here, you better fix it so it's storing the correct heights, right? You got to figure out what your loop invariants are and maintain them, right? So if this is our picture, and they say insert 12, so you insert 12. And you'll see that what's happening is all the heights, did the heights change already? No, they're going to change, right? 12's now of height 1, right? So 11 has become, right, the path up all got 1 longer, right? Stuff over here is not going to change, right? It's just things along this path, all those numbers are going to increase by 1, right? So to maintain that loop invariant, you're going to have to go bubble back up, go back up the path backwards, increasing all those numbers by 1, right? Everybody buy that? But we also have to make sure it stays an AVL tree, right? So we're going to move back up and see where the first bug is, right? So 11, is 11 happy? Yeah, 0 and 1, right? Is 2 happy? Is this 9 guy here happy? Yeah, this has height 1, this has height 2, right? 9's happy, right? Is 13 happy? That's height 3, this is height 1. 13's not happy, right? So you follow the path up, and you find the first node that's not happy, right? And then you think about the previous guy and the previous guy, all right? So here are 3 nodes. The 13, because it's the unhappy one, and the previous in the past is 9, and the previous is 11, right? So, all right, so we have our 3 this shape, right? But they might be this shape, right? They could be various shapes. I tell you, it's not likely to be this shape, right? It's going to be a shape like that. And what are we going to do? We're going to turn these 3 nodes from being this shape to being this shape. right? That's why I said I don't think it's the shape, because we wouldn't be able to fix it, right? So if it's this shape, we're going to turn it into this shape, right? So let's give these guys names here. Who's the smallest of these three? No. This one's smallest, right? And then this one, and then this one, right? Everybody buy that? These all have to be smaller, right? These are on the left, so that guy's got to be the maximum, right? And then this one has to be bigger than him. Or you can think about it reading it kind of this way, right? Everybody get those three ordered? So if we have those three ordered, now what order do they go in here? They got to go in that order, right? So whatever number you have here gets moved over here, right? Whatever number you have here gets moved up there, right? Everybody buy that? You're drawing the new picture. All right. So now there's all this stuff below. So what's down here is kind of, you know, is smaller than 1, right? And what's in here? This is from 1 to 2, right? And what's down here? 2 to 3, right? What's down here? Bigger than 3, right? So you got all these trees hanging. And where do you put them? Well, down here, you put, smaller than 1. Here, you put from 1 to 2. Here, you put from 2 to 3, right? Here, you put 3 bigger, right? So we did it, right? Everybody buy that? Now, you have to check, have I maintained the loop invariance, right? Double check to see if you've screwed up. You look at this and you say, is it a binary search tree, right? Well, we got 0, 1, 1 to 2, 2, 3, 2 to 3, 3, 3 on, right? You just quickly check. Is it a loop? Is it? And you say yes. And then we have the invariant. And here, let's jump over, right? So you check those, and then you rotate it, right? And then you say, oh, look at, we have all those numbers. The numbers have to do with the heights, right? You could think of fancy code for moving, adjusting these heights, but we're doing it just ourselves with paper. So just give me the heights, right? What height is this tree? I don't know. What height is this tree? What height is this tree, right? You just eyeball it and give the heights. And you know they're not going to be changing by, you know, it's going to be a nice pattern how it changes from there to there, that if you needed to, you could code it up, right? And then you check, oh, did I do it right? Is it an AVL tree, right? Is the difference between this height and this height at most 1? Is the distance between this height and this height at most 1? And check if you did it right. And if it's not, then fix it somehow, right? Everybody get that? Yeah. And yeah, I think that's what else I was going to say. Yeah. Everybody good? Yeah? Yeah. Yeah. So the 13 is the first mistake. And then the previous 2, that gives you, and that happened to be this shape, right? It could have been this shape, in which case this is 1, 2, 3, right? Whatever it is, those 3, you balance those 3, right? And you hang the pieces off the bottom. Done. Yeah? Good question. brilliant question, right? So the guys who came up with this proved that this technique for inserting will always give you an AVL tree, all right? So we didn't prove that. You won't prove that. Let's just believe it. And if you come up with an example when it's wrong, then somebody did something wrong, right? Now, if we're deleting something, then you go up the tree until you find the first mistake, like this, and you do the rebalancing. Right? Now, this will be an AVL tree, but there might be another mistake higher up. And then you have to go up further and find the next mistake and balance. And then you have to go further and find the next mistake and rebalance. All right? So if the maker of the exam was mean, they would make you do a deletion where you had to do a couple rebalances on the way up, right? If they're nice to you, they'll give you an insertion, and you have to do one. Yes? I'm going to say, in all my past tests, I've been nice, but I can't tell you what other people are going to want to do. If they give me a picture where it's a deletion and it's 3 rotations, I might say, sure, let's do it. Right? I certainly won't say, I didn't teach that. I'll say, hey, that's harder. Do you want to do a harder one? And they say, yeah, let's do a harder one. Yeah? All right, so I'll have to be honest with you. In the past, class sizes used to be 40, 50, and I used to do all the exam marking. And then during COVID, the class sizes got up to be 60, 70, 80, 90, and I got old and lazy. So I don't do all the marking anymore. But the TAs are going to be split. So the TAs who are marking ours, I'm going to have my own marking solution. So they're going to read my marking solution and mark it the way I talk to them. Good? Yep. Absolutely. Absolutely, right? And here's an experiment you could go out. Go to somebody who works at Google who's going to give you a job interview. And if you say, hey, I'm doing recursion and I'm going to give my left subtree to my first friend, they're not going to panic. They're going to figure out what you're talking about, right?